Hello and welcome. I am Nandish. Today I'll be presenting the Capstone project which I have done as part of the IBM Advanced Data Science Specialization. The dataset used for this project is taken from Kaggle. Each entry in this dataset consists of title, text, subject, and date. In this age of information overload, the fake news are flooding our society. Some group of people are easily influenced by these fake news and they believe it's true. So it is very important to differentiate these fake news from what's real. In this project, I attempt to build a classifier to classify news as real or fake. How to deal with these fake news? To answer this question, I'll be training a supervised machine learning model to flag these news as fake. The supervised machine learning model can be trained using traditional algorithms or deep learning approach. The architectural choices which I have made for this project are shown in this slide. Pandas to handle the data, NLTK toolkit to pre-process the data, scikit-learn to extract features and train model, pixie dust and seaborn for plotting, TensorFlow to train deep learning model, Watson machine learning service to store the model, finally TensorFlow model server to deploy the model. For this task, I am interested only in columns label, title, and text. So I will check whether there are any empty values present in these columns. As shown below, there are 0 empty entries in both real and fake news dataset in all these 3 columns. There might be sentences which are formatted differently. These will be taken care when doing pre-processing. During pre-processing, the data will be cleaned, tokenized, and lemmatized. During cleaning, punctuation marks, single character words, stop words are removed, and the words are lowercased. During tokenization, each sentence is converted into a list of words. During lemmatization, each word is reduced to their base word. For example, the word better as good as its lemma. Text data requires special preparation before you can start using it for predictive modeling. The text data must be parsed to remove words called tokens. Then the words need to be encoded as integers or floating point values for use as input to a machine learning algorithm called feature extraction. I'll be using count vectorizer as the starting point. The count vectorizer counts the number of times a word appears in the text and converts them to a count vector. Word count are a good starting point, but they are very basic. Later I'll be using TF-IDF based vectorizer. TF-IDF stands for turn frequency and inverse document frequency. Turn frequency summarizes how often a given word appears within a document. Inverse document frequency downscales words that appear a lot across the documents. I'll be using a classification accuracy and F1 score as model performance indicator. Classification accuracy is the ratio of number of correct predictions to the total number of input samples. It works well only if there are equal number of samples belonging to each class, as in this case. The real problem arises when the cost of misclassification of minor class samples are very high. If we deal with a rare but fatal disease, the cost of failing to diagnose the disease of a sick person is much higher than cost of sending a healthy person to more tests. F1 score is the harmonic mean between precision and recall. The F1 score ranges between 0 and 1. It tells how precise the classifier is as well as how robust it is. High precision but low recall gives you an extremely accurate classification, but then it misses a large number of instances that are difficult to classify. F1 score tries to find the balance between precision and recall. To begin with, I'll be using a naive-based classifier. This is a simple naive classification method based on Bayes' rule. It relies on a very simple representation of documents called bag of words representation. Since long time this classifier has been used for text classification tasks like email classification. Imagine we have two classes, positive and negative, and our input is a text representing a review of a movie. We want to know whether the review was positive or negative. So we may have a bag of positive words and a bag of negative words. We may then count the number of times each of these words appear in the document in order to classify the document as positive or negative. This would give this would be a good choice for starting as base model for this task. Later, I'll be training a deep learning algorithm using the following layers. It will have a word embedding layer to represent each word as a vector and three dense layers with activation and dropouts. And final layer will be a two-layer dense layer with two units and softmax activation. I'll be using categorical cross entropy as loss and Adam as optimizer. Now let's switch to the notebook and look at how this is implemented. At first, I'll install all the required libraries and set up the environment as shown in the first few cells here. The use case and the dataset are as I explained before. Assuming that we continuously get this data every day, IBM Object Store would be a perfect place to store these kind of large unstructured data at very low cost. So I have saved this dataset in IBM Object Store. I will be downloading this data from Object Store using pandas. This will be read as a pandas data frame using pandas read CSV function, and I'll be adding labels to this dataset. The following few cells shows the data quality assessment which I have done. As I have said before, there were 0 empty entries in both real and fake news dataset. During initial data exploration and visualization, I look into few of the real and fake news dataset. Now let's combine the title and text to create an article. Now let's see how the word count for real and fake news content looks like. As seen in this word cloud, the word featured, image, Donald Trump, even, said, also. These words appear more frequently in fake news. And in real news, Washington, Reuters, United States, White House seems to be appearing quite often. There are several ways in which these word counts can be improved, which we will be implementing during feature engineering. Common techniques like removing the common words, stemming, lemmatization, and further text cleaning will be used during the pre-processing. Let's add fake news data and real news data to create the dataset. Here I'll be shuffling the data and I'll drop the title and article column. Let's look at the percentage of fake news and real news in the dataset. They appear to be almost equal. The fake news dataset consists of 23,481 articles, and there are 21,417 articles as real news. The following few cells take care of the feature engineering. Before doing feature engineering, let's do the text pre-processing. In the text pre-processing, I'll be using a reject space tokenizer to extract words, and I'll be using a wordnet lemmatizer. At first, each sentences are split, and then each sentences are further split into uh, individual words, and then these individual words are lowercased, and some commonly appearing words called stop words are removed, and single character words are removed, and each word is lemmatized. As we have talked about the TF-IDF vectorizer, let's look at how the term frequency and idea inverse document frequency works. Here, here I have implemented a simple term frequency and plotted the top 25 occurring words in the dataset. The most occurring word is said. The inverse document frequency will address the issue which happens with the most occurring words. The below these three cells shows how inverse document frequency can be calculated. As we can see from the above plot that the rarely occurring words have higher IDF scores. Now let's plot IDF for top 25 words according to turn frequency. The words said which appear most of the times have lower inverse document frequency as shown here. Now it's time to create test and train data split. Before we do that, let's convert the categorical labels to numeric forms. The fake label will be transformed to 1, real label will be transformed to 0. And we do the test train split here. Test set consists of 35,918 articles and test set consists of 8,980 articles. The model performance indicators, as I have explained below, I'll be using classification accuracy and F1 score. And as an initial model, I'll be using a naive Bayes classifier, particularly multinomial naive Bayes, which is a specific instance of naive Bayes. In the first iteration, I'll be using a simple count-based vectorizer and a multinomial naive Bayes classifier. Let's see how this model performed. As you can see from the model evaluation, this model performed not bad at all. This model gave us an accuracy of 95% and F1 score of 0.95. The classification, the precision and recall are summarized in the classification report here. Now let's plot the confusion matrix for this model. This confusion matrix summarizes the false positives, false negatives, as well as true positives, true negatives for the model. In the second iteration, I will be using turn frequency, inverse document frequency based vectorizer and a Bayes classifier. And now let's see how this model performs. As you can see from the accuracy score and F1 score, this model was not much better compared to the previous version. Now let's train a deep learning model and see whether it outperforms both of our previous traditional algorithms. Before we build our model, let's transform a white train and white test into one not encoded vectors of length number of classes, which is 2 in our case here. So this is how the label looks before we transform it into one-hot encoded form, and this is how the label looks after it is being transformed into one-hot encoded form. So this will be our real data, real label. This will be our fake label. Here I'll be using a text vectorization layer, which is a new layer in TensorFlow 2.0. This layer takes care of uh, vectorizing the text data and pre-processing it. So here I have defined the maximum feature, which will be the vocabulary size as 30,000, and max length to 200, which will be the output sequence from this vectorizer layer. After I define the vectorizer layer, let's use adapt method on the trained data set to build the vocabulary. Now let's define the Keras model, which will use this vectorizer layer. And let's add few dense layers and activation. This model consists of an embedding layer, which embeds each word into a 100-dimensional vector, and 3 dense layers with 128, 256, and 128 units. And at the end, a dense layer with softmax activation will be used as a classifier. Let's compile this model using Adam optimizer and categorical cross entropy as loss. Let's summarize the model. This model consists of 5.6 million trainable weights which will be trained. Now let's define the batch size and train the model. And let's see how this model performed. As you can see from the model evaluation, this model significantly outperformed both of our previous iterations using naive-Bayes classifier. Also, training this neural network model was way faster compared to feature extraction plus training traditional naive-Bayes model. Considering these 2 points, obvious choice is deep learning neural network model, as we don't have hard restriction on size of the model. As usually, neural network models tends to be large compared to traditional machine learning models. Now coming to the model deployment. Before we deploy the model, let's persist the model to the disk, which I will do using the model.save, and I'll save the model in TensorFlow format. Let's zip this model into a tarball format, and I'll be saving this model. I'll be exporting this model to Watson Machine Learning repository, which I can use at a later stage. When required, the model exported to machine learning service can be downloaded. Unfortunately, Watson Machine Learning Service doesn't support the TensorFlow 2.0 version which I'm using for this task. So I'll have to go with the TensorFlow model server. TensorFlow model supports both CPU and GPU based model serving. It exposes 2 services as endpoints. The first endpoint is gRPC endpoint and the second endpoint is a REST API. Using the following commands, the TensorFlow model can be deployed, or by using the Docker container. This can also be deployed on a Docker container using this command, using the command shown below. Now sending an inference request to this model server is a simple REST API call. We make a post request to the exposed API using the data on which we want to do the inference. Now, for the purpose of this presentation, let's just use the trained model in the notebook environment and make the prediction on some of the news which I grabbed from reliable source. As you can see, when I did this prediction, it correctly classified this data as clean. This notebook demonstrates the typical workflow in any data science project. A real data science project will have several iterations over this workflow to optimize the performance of the model. For example, during model selection and during hyperparameter tuning after a model has been selected. Nevertheless, this project gives a strong understanding of steps taken and decisions taken in each step on the way to build a strong data product. This concludes my presentation. Thank you.